Hello, Videsh. Am I audible?
Yes, sir. Yes, sir.
Okay. কোনটা দেবো আগে দেখে নিয়েছো? কি আছে? 20 সেকেন্ড, ঠিক আছে? 20 সেকেন্ড বাদে হবে ওখানে। গল্প তো হয়ে গেছে। হ্যাঁ, কি হয়েছে? না ঠিক আছে, ইউটিউব থেকে এবারে 20 সেকেন্ড লাগবে। হাত করে তো পড়ে যাবে। একটু ঘন্টা করে নাও দাদা। Okay, we shall start within 2 minutes at 8:45. এত ডিস্টার্ব করছে না আজকে, আমার দম বের করে দিচ্ছে এখানে কাজ করতে। ওকে PowerPoint কই? Stop share. এটা সাউন্ড মেরে দে, সাউন্ড কমিয়ে দে। একটু কোনটা আছে দেখি একটু। জল নাই যে? ভালো লাগবে না। So welcome participants to the 5th lecture of the lecture series. So in the last lecture, I discussed about the characterization processes of nanomaterials. Mostly I have discussed the X-ray diffraction to study the crystallinity of the material, types of unit cells, particle size, strain, etc. Actually, that is the first check we should go for whether a sample have been prepared or not. So we should first go for X-ray diffraction checking that okay, our crystalline structure is formed. Then we shall go for other characterizations, and we have to first analyze the entire X-ray diffraction pattern, because we have to find out the type of unit cell, if any kind of distortion is there, dislocation densities, particle size is there, etc., etc. That I have already discussed in my earlier lecture. And then we should go for surface morphological studies that mostly include the electron microscopic image, the ACM and TEM. So last lecture I discussed about the scanning electron microscopy, where we saw that a high energy electron beam is focused on a sample, and the scattered electrons are collected by different types of detector, backscatter detector, secondary ions detector, etc. And then by considering the scattered amplitude and phase of the wave, the scattered wave, we can form the image. So I'm now showing you a video here that will give you the entire idea of the system. Although I discussed, but I think this video will help you to understand the basic process. So let us see. Okay. So this is this is actually the electron gun of the ACM. As I have shown, this is some hairpin type gun. So this is the gun of the ACM, and we apply a very high potential here, and as a result, electrons are emitted from this electron gun, and these electron guns are then accelerated through this cylindrical anode, so that this get a shape, so that you see these diverged electron beams are stopped. Only the focused beam will pass through this system. And then we have another column lenses, like several kinds of magnetic lenses, to focus all these electron beams onto the sample. So if I skip this part, if you see that this electron beam scans over the sample surface, and secondary electrons and backscatter electrons are generated, and these backscatter electrons are collected by the detectors, and we have the information we have the information of the phase difference between two. These three parameters are sufficient enough to form the image by fast Fourier transformation process. Okay, so here I am showing the operational procedure of the ACM. You see, this is a metallic sample. Okay, this is a metallic sample. That's why we do not need any kind of gold coating. I have already mentioned in my earlier class that if the surface is not conducting, then you have to coat with gold for ACM. As this is a metal, so we do not need gold coating. Now here, using this forceps, we are just making a scratch over this metal. We are just creating a sketch over this metal, and now let us see in the machine. So this is actually the ACM setup. Actually, the setup varies from manufacturer to manufacturer, the looks, but the entire inner system is same. So this is the sample chamber. You see, the sample will be inserted over here. Okay, and now it's getting in The sample is getting in, and then inside is the camera. Camera, there you see the sample. Okay. So this there is a camera inside this chamber so that we can check whether it's properly positioned or not. Then after properly positioning, we can adjust different kinds of parameters like the vacuum, the beam current, etc., etc. You see the specimen current, ion beam current, chamber pressure, etc. We have to maintain all these parameters for successful operation of the equipments. And then by varying this parameter, we can control the image formation. And you see, this is the screen, computer screen, interface with this ACM machine, this equipment that basically used to grab the picture, grab the ACM image. You see, this is the sketch that artificially created over the metallic sample. Now you see the scratch is clearly observed. You see several kinds of sculpts are already there that we have made, and you see the scanning is going on. You see this side is his, and this side is cleaning right now. So the scanning is in progress. So I'm just skipping this part. You see, this is complete, and save the image like that. So this process, this is the process actually, scanning continuing, different types of magnification on or adjusting of different parameters, so that we can get a fine image, and we can control various image parameters to get the desired one. So here you see a high magnification is doing this, the sketch we have made over the metal surface. And you see you can move the sample also. Here this is the sample order. This is the beam director. Okay, so now let's go to the next part, next type of imaging, which is known as the scanning tunneling transmission electron microscope, or TEM. In ACM, we can observe only the surface property of the material. That means we can observe only the surface morphology of the metal itself. But there are any kinds of defect inside the material that cannot be studied using ACM, because the electron beam is not entering into the sample. As the electron beam is not entering into the sample, we do not have any kind of information related to the internal structure of the material. That's why we should go for the transmission electron microscopy. So the name itself suggests that we must have the electron beam to transmit through the sample, and the transmitted beam will be collected in a detector, and those are transferred via Fourier transformation, and we shall get the image. The beauty of transmission electron microscope is that its resolution is very high compared to the ACM. And obviously, as it is a transmitted, we can have a more fine detail of the structure, like stacking faults, several kinds of defect, other critical layered formation, etc. That will be clearly observed from this TEM also. Okay, so let's get in to the basic principle of the transmission electron microscope. Actually, this is also the principle of ACM. So the electron optics is very much important in any kind of electron microscope. So first of all, let us see, whenever we have an electron beam accelerated through a potential V, the energy of the electron beam is EV. Okay. Now, as this the electron with this energy E, the de Broglie wavelength will be approximately lambda equal to h over root twice m0e into 1 plus e by 2 m0 c square, where m0 is the rest mass of the electron and E is the energy, that is E to V. charge of the electron multiplied by the accelerating potential. Okay. Okay. So now there is a limit, which is that I have already discussed, the limit of resolution. That is the maximum separation that can be observed in electron microscope. So as you have already discussed in optical microscopy section, in the very first section, that this D is proportional to the wavelength. So if the wavelength is smaller, then this wavelength, this D will be small. That means the smallest difference or small particles can be distinguished properly. So that's why we have to energize the electron beam to high energy so that we can have a very small wavelength and we can distinguish very small objects. So that's why you use the potential about a few thousand electron volt, 10,000, 20,000, 50,000 volt is applied to the TEM. So now let us go to the instrumentation of TEM. Okay. So this is the basic layout of up to this part. It is identical. We have an electron gun, and the electron gun might be harmonic type, single crystal lithium hexafluoride due to field emission. That may be. That depends on instrument to instrument. And when the electron passes through this, there are condenser lenses, and anode is not shown here. There are condenser lenses to focus all these electron beams. Now, these electron beams will pass through this scanning path so that we can have the information about the initial beam parameters. After this condensation, it incident over the thin sample. You know that in a transmission electron microscope, the electron beam must transmit through the sample. So the sample must be very thin in this case. So when the sample incident, the electron beam transmits to the sample, and there we have objective lens and other projector lens, intermediate lenses, etc. to optimize the beam parameters, and the electron beam is now allowed to incident on a fluorescent screen to produce the image. And there are also several electron detectors and CCD for detect these images also. And here we have another X-ray detector is placed here. This is because when the electron beam interacts with the sample, it may produce X-ray, and this X-ray will give you the information about the composition of the sample that I have already discussed in ACM also, that energy dispersive X-ray spectroscopy. Okay, so now here is the actual equipment. The basic system varies from system to system, but this is the basic equipment for electro-optic column, and this is the place where the sample will be inserted. To open this lid to see the image. So I've already mentioned that as the electron beam will transmit through the sample preparation is very much important here. Okay, preparation of the sample is very much important. So I'll show you a video over here which will discuss the sample preparation technique. Just wait for a minute. I'm just sharing the video for sample preparation. কত সুবিধা সেটা যা দিবে সব দিয়ে দিবে। Screen. Okay. Here you see how to prepare a sample, because sample preparation is very much important in TEM. That is actually the fundamental step of TEM to get a very good image. So this is basically where the grids will be placed. So this is a copper check. This is a copper grid coated carbon, copper mesh-like structure. The diameter of it is about 3 millimeter. Okay, there are lots of mesh, and this is coated with carbon. Once this is, so the grid is placed over here, and sample will be put over it. I'm just skipping this part. The grid is now being placed over is nothing but a carbon tape, so that the grid is stick to, because this grid is very, even your breathing is enough to flow it off. So we have to do this very, the grid over here. We have the sample. Let me mention one thing, that to sample, suppose if you have a sample, you have to disperse sample and ethanol, and you have to process it ultrasonication, so that the particles or rods, whatever be, those get dispersed ethanol. A drop of the sample is put over this grid, so that when the ethanol is evaporated, the sample will be limited over this grid. Now this sample needs to be placed on the ICM. We are just soaking the excess ethanol or water using the and so this is sample is now placed securely. So this is the basic process of with SCMA sample. Now also how this TEM work. Okay. I'm sharing another video that will discuss how this TEM work actually. So before going to that, I must show you sample holder that I showed over there. That copper mesh, how it looks like. The mesh is like this. Okay, you see, this is the copper mesh actually, over which the sample is to be placed. This is the diameter is 3 millimeter and it's very thin. And over this, we have these are the mesh like this, and over this mesh we have a carbon coating. Okay, a carbon coating is there over this TEM grid. So after that, I am showing you the video how this machine actually operates. That will give an idea, brief idea about that. Hello, am I audible? Hello, Videsh, am I audible?
So facing network problem.
Actually, network problem is. I think now the problem is solved. Okay. Hello. Now can you hear participants? Can you hear me? Hello, everyone. Can you hear me?
Not clearly.
Okay, let's see. This is a video demonstration of the transmission on microscope, and as I have already said, that after entering into this condenser lens scanning pass over, and here is the sample it transmits to this, and it will be formed at the bottom over the fluorescent screen. Now I'm going the actual instrumentation. Now you see, this is the sample holder, and this is the grid that is being placed. Okay. This is the grid actually on samples are placed on it. Now this grid will be inserted into the tube. How it's being mind that this electron column is evacuated. Okay, and we have to enter this sample into it, and we're just putting liquid nitrogen over here. জয়েন করতে মুশকিল সাউন্ডটা okay. Liquid nitrogen is over here. Now we have to insert this sample through this portion. we have several buttons are there to control the entire thing, like the pressure within the chamber, etc., the accelerating voltage, etc. Now, once the things are ready, then we have to insert the sample into the tube. Okay. So the sample is being inserted partially, the system will be locked, evacuated, and it will be inserted. So this is the red. When this becomes green, then we have to press it up to put the sample into the electron beam, into the path of the electron beam. Okay. Now the sample is on the path of the electron beam, and now the electron beam will be started to uh, study the image. So these are the some kinds of focusing arrangements are there. You see, this is the fluorescent screen over which the image is forming, and we have to control these several parameters like intensity, stigmator, etc., to control the image. Okay, so this is the a kind of diffraction pattern, and we have to focus these. So various controls are there to form the images. In fact, we can clearly see the image over here also, but for better visibility, we have to transport this into the machine itself. So let's skip this part, this section. Yeah. Okay, after controlling all this, the entire thing will be transmitted into the screen. So that is actually the fundamental issues related to the transmission electron microscope. Next second. Okay. This image basically shows a transmission electron microscopic image of nano. You see, cubical structures have been formed. And this is the scale of 50 nanometer, from which we can find that the size is approximately 20 to 25 nanometer. Another sample. This is actually zinc oxide nanoparticles, transmission electron microscope of zinc oxide nanoparticles. Now, what is the beauty of TM? You see that you can clearly see the crystal lying under this crystal also. This is a crystal sitting over this one. But if it is ACM, then you cannot see these in inner portions. We can see only the upper part, so that this section should be blocked. So this is the beauty of TM, that we can study the entire internal structure of the crystal, and you can also find that these hexagonal crystals are formed. Those are basically the hexagonal unit cells of zinc oxide. This is the low magnification TM of the same sample. And you see the sample, you see the lattice planes are quite clear. Okay, so if there, you see the here is a sudden unstacking or breaking of the structure over here. So these are the things that can be clearly observed from TM that is not possible to study in SEM. Okay. Here this is a nanorod is laying over here. The lattice hinges are there, and we can find this difference also, this lattice spacing or D spacing from this scale bar also. Actually, this can be done with the software sheet we already etc. So what I say that this lattice planes are clearly observed. Any kind of dislocation defects can be easily seen. This is the image of zinc oxide quantum dots, and here you can see clear images of particles are found to form of diameter about 2 to 3 nanometer, and the lattice patterns are there. observe the dislocations. You see, this is one kind of lattice pattern. This is another kind of lattice pattern. So along this line, there are lattice mismatch. This is a silicon substrate, and this is gallium arsenide. Okay, yeah, gallium antimony. So at the interface, a huge lattice mismatch happens that leads to dislocations. Here, these dislocations have been formed at the interface of the two material junction. There are some other kinds of TM image where we can study the detailed crystal structure. This is another one. This portion is like this way, and in this portion, so you can clearly observe the change in the lattice arrangement pattern also. For example, the next one is showing a sample is moving. This is a magnetic cell. When an electron beam incident on this sample, of the magnetic sample with this electron, the sample gets drifted. That's why this moving ডিস্টার্ব হচ্ছে আজ আমাদের ল্যাপটপ হচ্ছে না এটাও ডিস্টার্ব হচ্ছে another kind of microscopy, that is scanning tunneling microscopy. It will be used to study the surface behavior of the material. This is scanning tunneling microscope. Okay, let's see what that. Name is that the tunneling problems in this streaming. To solve this. আমি তো কিছু বলি আমি বুঝতে পারছি just wait for 2-3 minutes. Let me check the network issue happening. Just wait for 2-3 minutes. Okay. Yes. So let me start once again. So scanning microscope phenomena is occurring over there in the microscope. Okay, let's go enter more into STM. I just thought we can only image the surface of a material. Okay, we can image the surface of a material, and it has a very high resolution. If you see, the resolution limit is 0.1 nanometer lateral resolution, and depth resolution is also 0.01 nanometer. So that we have practically scaled down to atomic level resolution. Okay, so that is the beauty of this microscope, that it offers us a very high resolution. Here is the basic tunneling phenomena. You know that you have a potential barrier, and if an energy is incident on a barrier, and if the energy of the electron is not sufficient enough, that means if the energy of the electron is less than the barrier potential, classically it is not possible to obtain the electron outside this barrier. Okay, suppose you have a large wall of large height, and you throw a ball. If the energy of the ball is not sufficient enough to overcome the height, then obviously the ball will be scattered back from the wall. So the ball will not be able to go on the other side. But in quantum mechanics, the situation is different. There is a possibility of the electron to have on the other side of this potential wall. So that is what is called quantum mechanical tunneling, and this tunneling phenomena is being used. This tunneling phenomena is being used to image this surface. Okay. So this is the basic layout of the STM. So what this is a sample. This is the scan tip. Okay. So this is usually a tungsten tip, and a piezo controlled light controller is there, and as computer operated, and it has, so the current will be flow, and that current will be recorded to study the surface. So this is the scanning tip is, as you mentioned, this is made of tungsten or atom. And what is the beauty of this STM is its resolution. So before going to that, let's see how it's works. Suppose this is the tip. This is the tip I am showing atomic level over here. So this is the tip, and this is the sample. And the tip is biased with respect to sample. When the sample comes very close to the sample surface, no, it will not touch the sample surface. It is very close to the sample surface. Then what happens, that tunneling current tends to flow from the sample to this tip. Okay, tunneling current will flow from sample to tip, and this tunneling current is recorded to study the image, surface image. And this tunneling current has basically due to the change of states and voltage, etc., etc. So the imaging is usually in two methods. One is constant hide mode, and the second one is constant hide mode. So what is that? So this is constant current mode. What is it? So this is our sample surface. Okay, this is the rough surface of the sample. You see, and this is the scanning tip. We are saying the constant current mode. That means we keep the current constant. Okay. Suppose the scanning tip is here. Suppose the tip is not here. Suppose the tip is here. Okay. And this is the location of the tip. And if a certain gap is there, the current will be flowing. As the tip moves towards this region, now the gap has decreased. So as the distance has decreased, the tunneling current will increase. So to keep the current constant, we have to move this tip up, so that current again becomes takes its place. Okay. So That is a piezo scanner. I have said that how much distance we have to move this sample, this material. This height will give you the surface roughness. So this is the constant height mode and another constant current mode. Another mode is there that is called constant height mode. The scanning height is kept fixed. So this is sample surface, and this is the scanning depth. In the scanning, it scans over this line. So height is fixed. So when the tip is here, the distance is large, the current is small. When the tip is here, the distance is small, the current is large. So the current is basically proportional to this surface. So by studying this variation of current, we can see the surface morphology of this STM. Okay. So in scanning over the sample, we can also obtain the electronic structure sample by switching this voltage to this particular location. So that is one kind of spectroscopy which is called scanning tunneling spectroscopy. And from this scanning tunneling spectroscopy, we can find the local density of states and the defects, impurities in the sample. So how will the image look like? So this is the ST image. You can see the surface atoms like this. So this is one ST image, and I'm showing another ST image over here. You can see aluminum atoms. This is basically carbon C60. The ST image of carbon C60, and there are some other accessories by which this STM can be used for multiple purposes, like scanning tunneling microscopy that can. There we can use an optical tip for the tunneling purpose, and scanning, tunneling, photometry, spin polarized STM, and AFM. So these are the several accessories that can be fitted with this STM to obtain different kinds of information about the surface. I shall discuss one more microscopy, which is the atomic force microscopy. This is another kind of microscope that is also used to study the surface roughness of a sample with high resolution. So okay, let's see the basic principle over here. This is as I said, this is not clear. So let's directly go to the principle. Suppose this is the sample surface. A half surface is there. We have a scanning cantilever tip. This is a cantilever. This is a tip. Okay. You see, this is the same image of the tip is like this, standard platinum tip. This cantilever will move over this surface, and this tip will touch the surface. Okay. So as the cantilever moves over the space, cantilever change is over this cantilever tip, and reflected ray is collected here. Now, as the cantilever moves over the surface, angle of incidence will change, the beam will change. By cutting those information, we can see the surface of the sample. So, using this microscopy, this is possible the sample hydration. We can also distinguish the sample based on its mechanical properties like hardness, surface roughness, etc. And we can also use this AFM for microfraction also. Suppose we have to do some atomic manipulation, we have to remove some surface atom, we have to add extra surface atom. Okay, so this type of advanced fabrication techniques can be done using this atomic force microscopy. So, in of identify can start between the atoms, neighboring atoms, so that we can have an understanding of the interaction behavior of the electrons, and also study various physical properties arising from this change of electronic arrangement or the surface identification of atoms. In case of biology, we can distinguish cancer cells from the normal cells, because you see all these interesting things depends on the electronic states of the surface atom. So in a healthy cell, the electronic density of state will be different from that cancerous cell. So we can distinguish a cancerous cell from a normal healthy cell, and we can also find or study the depth of interaction between a specific cell and the neighboring cell in a competitive cultural system that have been made through the biological process. This is the AFM image. You can see here these particles are there. You can see several rod-like structures are all there. This is the AFM image of zinc oxide nanoparticle doped with SN position. You can see the change in the particle size also. And this is the AFM image of zinc oxide nano rods. Okay. This is the rod-like structure, as you can see from the structure. Okay, so these are more or less about the optical spectroscopy, not optical spectroscopy, optical imaging, and optical spectroscopy also of in materials characterization. Also, several other processes there to study the surface characterization, but these are the most commonly available and easy method for studying the surface structure of the material. And one thing I must mention over here, that we are saying that these methods are simple methods. Okay, the methods are simple, but one thing you must remember, that the equipments are very costly. Whatever the instrument we are using in this method are very costly. If you see, if you go for an SEM or TM, the budget is about few crores. Of course, the FM is the budget of FM is a little bit small, but that is a main constraint characterization techniques, and defined study the surface morphology of the sample. So I think today I should stop here, because a lot of network problems, etc. are there. So I will try to make another recording, record of this lecture, and upload in the YouTube. And I will also send you the video link, so that in due time you can also check that video also. That will be freshly recorded. There are no problems will be there. Okay. So if you have any questions, you can just unmute and you can directly ask. If you have any question, you can unmute and you can ask, or you can also put your question in the Zoom chat box also, and YouTube live chat box also. KJ? If you have any question, you just unmute and ask directly. Or even type in the chat box also. Because I think there was a lot of disturbance in today's lecture. So obviously, I will put a fresh recording. I will freshly record this video and put in the YouTube, and I'll share the link with you also. If you have any question till this part, I'll discuss it. So one question is there, what is the difference between SEM and TM? Okay, so scanning electron microscopy provides you only the surface morphology of the material, whereas in transmission electron microscopy, we can have the internal informations of the material also. I mean, you can find the crystal structure, actual shape of the unit cell. Suppose if you in ACM you find a nanoparticle, a spherical particle. But what is the type of unit cell that you can predict? But you can study the unit cell by using TM also. And in TM, in case of TM also, you can find detailed crystal structure, type of unit cell, and atomic arrangement of the atoms, dislocations, defects, etc. All these can be studied. That is the main difference between ACM and TM. In case of ACM, how can we distinguish the particles by wavelength? Okay, let me tell you. In ACM, we are having an electron beam that we are saying that wave that is incident on the particle and is scattering from different portion of the particle. That means scattering from the different portion of the atom. And as due to this scattering, waves suffer phase difference. And the wave coming from different portions have different phase. That phase is actually compared with the original incident wave of the electron. That was there was a scanning coil. Okay. And by comparing these two, we have some Fourier transformation and associated process by which, considering this phase, you can image the surface. One more thing at this point, I must tell you that we can do our laboratory very easy. In fact, you all of you have that biological slides, the cross section of the stem cell, leaf, etc. Okay, if you put a laser, like if you have this slide like this, you direct a laser this way, and you put a screen over here, a white paper, and you can see the image. Okay, now you place a polarizer on before the laser beam. So if you take the polarization axis like this, you find the image, you make the polarization cross and take the image. And if you superpose the image, if you have the phase information about this object, okay, from there you can generate also a three-dimensional image. Okay. Another thing is the escape depth. Escape depth means basically when we're talking about the secondary electrons, whenever the electron in ACM, the electron beam is interacting with the samples, that electron beam is penetrating more, then the secondary electrons that are generated from the underlayer of the material that have to reach the surface. If that thickness is sufficient enough so that it will be escaped, otherwise it will remain. That is what is called escape depth. Question is, what is the most effective? Which is the most effective constant current or constant height mode? Actually, both are done. Okay, both methods are almost equally effective, but for highly conducting sample, we usually prefer for that constant current mode. Otherwise, both methods are effective, no problem. But only in the case that if you move on in constant height mode, you constantly move the piezo scanner, piezo scanner, and that is that imposes some additional precautions regarding this mechanical readjustment. And in difference between STM or AFM, with AFM is that by STM or AFM, we can study the surface morphology, surface structure, and local density of set. But we cannot study the internal structure. But TM, the electron is transmitting through the sample, so we can study the internal structure of the crystal's material itself. That is very important. That is the beauty of TM. So is there any more questions? Okay. How can the cantilever be tipped when the light from the photodiode as well as the laser falling in? Everything is arranged or controlled by a microprocessor also. All the entire things are moving, and that adjustment is finely done. Okay, that is the technical issue related to this instrument. So is there any questions? So if you have any questions, you can also, I think there was a lot of communication problems. So in the meantime, you just check this video, and if you have any questions, you can email me so that I will answer through your email, or maybe in the next lecture, I will be able to answer this. And in the meantime, I'll prepare a video and upload in the YouTube so that you can firstly read it. So, and I have already shared the feedback link. So you please submit the feedback by 12 o'clock. And so in the next day, I shall be discussing about the optical properties of the nanomaterial a little bit, and then I shall solely move over to the environmental aspects of nanomaterials. That means the application of nanomaterials in agriculture and biological systems, and these nanomaterials, impact of nanomaterials on the environment when they are released into the environment, whether they produce toxic effect, whether they are compatible with the sustainable development or not. That issues will be mostly discussed in the next lecture. So thank you very much, and thank you, Arjun, for managing all this entire technical activities, and thank you all for your attention. So see you in the next lecture.